All right, good morning. Here we go with lecture number 21 on finishing up chapter 5 this week. I just have one, I'll send an announcement on the B course, but tomorrow's office hour I have to cancel. I'm going to travel tomorrow. I'll be there today and Thursday, so you won't really notice except for tomorrow. Let's see, I want to ask about the problem set, of course, because it's due in a week. More questions. Has anyone got it to spin around in a cool, physically looking way? It's working? Yeah. How do you know it's working?
Like you said, if we run for a long period of time, does the same gain or lose energy?
Oh, how do you know? You look at the energy, or it looks like it's preserved? Yeah.
If you run it for long enough, if you go too long, eventually it diverges too much from the differential.
Exactly. Yeah. That's how you do. These are very iffy because I don't know if you know it from dynamic. If you're taking classes in nonlinear dynamical systems, these are chaotic. So if you start like almost hanging, some of the initial conditions I gave just doing this, they are predictable. But if you do anything a little bit crazy, and it looks like it is completely deterministic, but if you perturb it by the tiniest epsilon, that's a perturbation that will be enhanced, and a certain time later it will deviate completely. It's like throwing a die. That if you just perturb the initial condition by epsilon, you might get a completely different outcome at the end. So yes, it's a little hard to compare. There's the reason I asked you for the convergence test in problem number 3, right? Then I have a fairly well-behaved, I guess we get away with it by having a fairly short time. Well, it's not that short. It's time 100. But it's case 1, which is a case where the pendulum is hanging, well, I guess it's 1 radian on each. It's not one of the most crazy cases. So there it works out. Anyway, I think if you make small mistakes, there are a lot of questions about maybe confusion about how I organize this, but I think many of you see that problem 1 is just a question of identifying the equations and writing f. Problem 1 is the equivalent of me in MATLAB. You know, I always do f equals this, right? And for my model problem, that's what I do, right? Your problem 1 in program assignment 3 is just doing that. But it's much more complicated because it's 4 equations and 4 unknowns, okay? I did mention that you should definitely create a function on the side.
So you want it as a MATLAB function?
Yes, exactly. So you want to create this f, but you can, of course, also, every time you create this f, let's say we call it f simple. You can, of course, also just do a function called f simple. And this is, I told you I don't do it in class because it takes too long, but it's the recommended way to do things. So then you can do this, and you can just do f is equal to y. Okay? So this is the other way to create functions in MATLAB. And of course, I can solve this with RK4 if I want to. RK4 of at f simple. Have you seen that notation? So these are the 2 ways to create. I often do the inline, which is when you just write it like that. You can, I don't think that's going to work well for a pendulum. Although in principle it will work, but it will be a big mess, right? So then instead you create a function, and you refer to it by at functioning. And this, let's try it. What were the parameters here? Starting condition and number of steps, right? Oh, yeah, so now I confused it by having it twice. There we go. So that was a simple example of what you're going to do. But of course, instead of these equations, you're writing an equation. Just remember here, y has 4 numbers. It's a vector of 4 components. 1, 2, 3, 4. F has 4 numbers, right? That's how simple it is. That's how we make this into a vector-based, a system of differential equation. And of course, those numbers are what you derive here in the first part of it. And you write a vector y with 4 numbers, and a function f that produces 4 numbers, which are the equations. Well, the team, but I know I'm confusing you. It's like, I mean, in a general package, there should be a t. We always put the t there, right? But if you look at this, I'm not using t. These are a special class of very important problems in physics that are called autonomous. They don't depend on t. So I just took it away. I mean, it's kind of silly. I think I'm just confusing you by taking it away. But at the same time, if you're writing your code yourself, and this function doesn't use t, we don't have to give it t. And you can see how much it's... So the truth is that if you do what I say, which is this, right? I tell you to do this. Then, of course, Runge-Kutta will fail because it's sending too many arguments to this function. How would you fix that? Either you don't do what I say and you add the t there, which I'm sure the GSIs are going to be perfectly fine when they grade. And maybe I should have done that. Just t comma y there and don't use the t. Maybe that's the easiest, right? But you could also write this, and I'm assuming, I guess I assume that you're going to write your own Runge-Kuttas. And if you know there is no t, it just simplifies this a lot because all of these guys go away. So that's another option. Since many of you are probably copying RK4 anyway because you want to plot it, you could do that and just remove those. It's kind of simple. F just doesn't depend on t. And whatever you want to do about it in MATLAB is fine. But yeah, problem 2 is actually quite easy. It's really, when you get part 1 right, it's almost just calling my RK4. That's how simple this is with these initial conditions. So there's not a lot of magic in this programming assignment. Any other questions? You'll know enough for programming assignment 4, the last one, after Thursday's lecture, actually. But I can post, so I'll post it by then. And it will be due, as you remember, 2 weeks after that. So I guess, yeah, last week. Anyway, let's cover stuff we have to do here. A huge part here, just quickly what we did last time was this error control. I gave you a function RKF, and that's what you do for the homework. I guess the homework that will be due next week, right? Let's see. That function is based on the following, that you create two Runge-Kutta methods of different order. One is called twiddle, the other one is not twiddle. Or it's just, one is called plain W's, the other one is called W twiddle, okay? So the twiddle is much more accurate, which means that if you make some appropriate assumptions, by subtracting the 2, you get a good estimate of the error. Dividing by h, you get a good estimate of the local truncation error, which includes an h divided by h in the definition. What's the power of this? It means that you can take a step and give an estimate on the error in that step. Okay? Based on that, you can control the time step. And this looks a little complicated, but it's really as simple as we said. If you know how the error scales with h, and you have an estimate of the error, you can change the step size so you get the error you want. My example was that you want epsilon 10 to the minus 3. You take a step, and epsilon is 10 to the minus 2. Okay? If it's Euler's method, clearly you want to divide h by 10. Now, if you have a higher order method, let's say a quadratically accurate method, you only need to divide it by square root of 10, right? Etc. And that's what comes out in this expression here. So it's a fairly simple procedure. The code there is a little complicated. We did go through it. You will, of course, use it as it is, essentially. It's not that complicated. It's a lot of numbers. Most of it was that it was super ugly because of all the numbers. But yeah. All these numbers make it really messy, right? But I guess the key parts was the idea that we had, and also confusing that I renamed it. But I think I followed the notation in the book, or maybe not. But it's clear that there is an estimation of the error. And there's some control logic saying if this error is less than what you wanted it to be, you do certain things. In particular, you accept the step. And that's what I do here. Otherwise, you just don't take the step. We always change the step size. And there were some hacks here. I call them hacks because it's not beautiful math. It's just things people figure out you have to do. Don't change step size too much in one step, etc. But that's about it. So it's good to see. I did mention that this is really state of the art. This is what people use in practice. There is a function in MATLAB called ODE45 that uses almost an identical method with very similar inputs and works in a very similar way. So this is what people really want. People have an equation, y prime equals f, and they want to solve it. And they really want a black box solver. And this is as close as we can come in the sense that there is not even a step size or number of steps. You just say, here's an equation, f. Here are some parameters. And then the only numerical thing you tell is essentially how accurate you want it to be. And I think you can all agree that as a user, suppose you're an engineer trying to solve this pendulum problem. I mean, in this class, you have to code it up. But if you're an engineer who really just want to solve the problem, this is what you want to do. You're just going to say, I want 6 digits of accuracy, just solve it. So it's pretty close. You should, sometimes in classes where it's a little school book problem, but this is really pretty close to reality. Anyway, then I started talking about multi-step method, which is It will parallel the Runge-Kuttas very much. It's just a huge, different type of class of solvers. And they have their own issues. So let's see what we have to say about that. We're solving exactly the same problem. The only difference now is that we're going to look at several times. Remember, everything we did with Runge-Kuttas started at ti and took a step to ti plus 1. We always had this setting that we're standing at ti, and we moved on to ti plus 1. It's a little hard maybe to see that we did it for the Runge-Kuttas, because sometimes we did all these intermediate steps, but really we just started at ti and did a bunch of stuff and went to ti plus 1. The big difference now is that I'm going to assume that you have ti minus 1 as well. Okay? And I'm going to say, now that I have these two numbers, I might be able to do something better in order to solve the differential equation, y prime equals f of t comma y. Okay? And of course, you can go further. And this is a multi-step method, because there are multiple old steps in order to produce the next one. All right? And we look at various ones of these. First, just in terms of the definition, it of course means that the next w can be written as a linear combination. This is actually a special case of linear multi-step methods, which are what we're going to use. So you see the next w can be obtained from the previous w, but also older ones, wi minus 1, I minus 2, etc. Okay? It can also use f's at these corresponding times. So you should see that Euler is a special class of this, of course. Euler is not a it's a one-step method, but it fits this pattern. If you set am minus 1 here to 1, and you set this coefficient here to 1, I think you get Euler's method. Okay? Now, clearly you want to play with these coefficients and get a bunch of other methods. But that's basically what you do. So there are various methods. Here are two listed, right? These are two, just to show what they could look like. A fourth order Adams-Bashforth. You see, I'm giving a lot of initial conditions. Why am I doing that? This is completely unmathematical, because the equation is fully specified by one initial condition. If it's Lipschitz, as you remember, there is a unique solution. So if you give W0 equals alpha, you've done everything you need to do, and you should be finished. But no, this method requires you to give a few more steps. And this is obvious because it's in order to get started, you need 4 numbers. And it's a big issue. It's a big drawback with these methods. Anyway, suppose you get started somehow. Then you can produce the next w from the previous one by, again, a linear combination of, in this case, just the f values at these points. That's the plan. Yeah?
What's stopping you from doing like an Euler step and then doing like the second order or something? You know what I mean?
You want to first do an Euler. The way you said it, it sounds exactly like the Runge-Kuttas. Remember I said with the Runge-Kutta that the midpoint method, we took half an Euler step like this, right? We got a new slope, and we took another step. That's what the Runge-Kuttas are doing. Here, I mean, Euler is part of this, but you want to do better. So it's not just, Euler really just computes the slope here and steps over there. But we're going to do other things. So it's more general. But of course, you can do Euler. Everything is included in this. It's a pretty general framework. Here's another method. You might notice that there's a f of wi plus 1 in the right-hand side here. Does that disturb you? Would you be able to implement this in MATLAB easily? So let me implement these, because I want to show you how to do it. And I'm actually going to do what I didn't do before. So Adams example. All right, so this is how you create functions. Let's see if we can implement this function, this method up here. And I'm, of course, going to do it on my trivial example that I always use. I guess I'm nowadays liking the minus 1 instead, so it doesn't blow up. And let's just do what we always do. We choose n, 10 steps. We go all the way to 1, right? Shouldn't that be a little n? And then we create a timeline that goes from like that. That's what we always do, right? And then we start somewhere. And then we have a loop. Let me do Euler first. 1 to n, and the next one is the previous one plus h times f of ti comma wi. And why don't we plot the result, okay? This is what I've been doing all the time, and I should have done it like a script like this, but I always did it on the fly in MATLAB, right? So if I didn't mess this up, example, it should produce the same old plot, but now I changed it to minus y because I like that better. Let's go a little further. Let's go 30 steps to 3. Oops. What did I mess up? 91. I've done something bad here. And I don't see it. Then you try to clear all. This is a big problem with MATLAB, that it has a history. And so it's supposed to be, why is my T 91? Your N affects, oh, of course. There you go. H is the width of the integration. If you really wanted this, you should have an A and B, right? You know, and I missed it, didn't do that. Good. So now I guess we got that. This is our test problem. Let's turn it now into an Adams method. This was just Euler stepping. No issues. You just give it the starting value, and it produces the next, and it goes all the way. We're now going to change it to this method here, where we produce the next value by, it's very simple. If you think about it, the first part is Euler. It's the old value plus something times f at the old value, right? So up to here, it's really exactly Euler multiplying this by 55 divided by 24. But then we need these older guys as well. So to begin with, as I said, that's a slight issue, that how do we get started? You need W0, W1, W2, W3 in order to produce W4. And this is a huge issue, and there are solutions, but for now I'm going to cheat. And I'm going to say I know the true solution, okay? So this is how I'm going to do it. The true solution is x of minus t, right? So I'm going to do that and take the first 4 solutions. All right, it's really iffy, but that's how we do just to test this method. When you've done that, of course, you're not going to start at 1. You start at 4, because there are 4 steps. And now you just implement the method. So let me do it. Can I have them at the same? Yeah, we can do this. All right, then you just code up here, h over 24 times f times 55 minus 59 of f times, and what am I sending is to this f? You see that I'm sending in 1 step older, right? That's what a multi-step method is. And then plus 37 times f of t of I minus 2. And finally, minus 9 times f of t of I minus 3. All right? Not too bad, right? The key part here is that you guarantee that when you're standing at I equals 4, you have not just w of I, but you have w of I minus 1 all the way down to w I minus 3. Then you can keep on going forever. Let's see if it works. I should have plotted the error with, well, it looks screwed, but why don't we plot the true solution on top of this? Well, it's insanely accurate. The error seems to be, I mean, it's less than 1/10,000. It's a very, very small error. But that's what you expect from RK4 as well. This method is very comparable. It's a 4th order accurate method. But anyway, the reason I did it was to just emphasize the issues in implementation. And I think to summarize, this is exactly the Euler script. It's a new method, of course. But the main issue that really strikes you is that you need to get started with many numbers, and you always look back a few steps in history. Remember Rangekata? You give it Ti or Wi, and you can produce Wi plus 1. To farm it, you don't need anything else. So that's how these methods work. Let me show you Molton. Let's save this file. I can post it on the web and do Adams Molton example. Let's see if we can implement this method. What's the problem with it? It looks almost identical, right? But there's a big difference. I mentioned it before. The difference is that f of Wi plus 1 shows up here. That means you can't just evaluate Wi plus 1. Is that a showstopper? What do you have to do to evaluate Wi plus 1? I'm saying you want to solve. You want to compute Wi plus. Remember, you know Wi. You know Wi minus 1, Wi minus 2. You don't know Wi plus 1. This equation is meant for computing it. But then in the expression to compute it, it shows up in the right-hand side. What does that make it? It's not just an expression for Wi plus 1, but an expression involving Wi plus 1 in complicated ways. It's an equation. It's a root solving. This is chapter 2. You have to solve it somehow. Of course, I'm not going to do that. But in general, you would have to plug in a whole Newton solver on this. But you know how to do this. If I told you how to solve an equation, you just have to keep track of what is x. What is the unknown, right? The unknown is wi plus 1. It shows up on both sides of this equation. Okay? But let's do it just for our test problem. So Adams Moulton for our problem y prime equals minus y. Then, of course, let me write the f. F of t comma y equals minus y. Then, of course, it's pretty easy, because then you can just move it over to the other side, right? So remember, it says that you must find a new wi plus 1 that satisfies this. Right? So it's plus h 24th times 9 f of ti plus 1 comma wi plus 1. All right? And the rest I don't care about. So it's because that's not the problem. You plug in what your f is wi plus h over 24 times 9 of, f is really just minus y. So this is minus wi plus 1, right? And these, you do the same, but I don't care because that's not the difficult part. Do you now see how to solve this equation for wi plus 1? Now it's easy because it's a linear f. So here is this just a number times wi plus 1. Move it over to the left, and you have to divide it out, right? Kind of annoying. But it's the way in principle, it's nothing difficult. So I guess this means that if you move to the left, everything involving I plus 1, you get this term here with a plus sign, h times 9/24 of wi plus 1. Right? Equals wi plus h over 24 of the rest that I didn't write before. And finally, you just divide it down. So wi plus 1 will be wi plus h24, and maybe it is confusing now. This is everything I did not take into account. So the I minus 1, etc., right? And then all of this divided by, what is that number? 1 plus 9h24. That's how you have to do it. Kind of annoying. Let's try. By the way, this method is, this here we call a 4-step method, the one we did, because it needs 4 points to produce one new. If you see here, it's only a 3-step method. So if I'm now going to create my file Adams Moulton example, let's just do 3 here and start implementing this. But as I said, you're going to have to do something like this. You're going to have to do the divided by 24, and then we skip this first guy, because that's when we move to the left, right? With a 9. So we start on the 19. So it's going to be 19 times that f minus 5 times that f plus that f. But then all of this had to be divided by that number. A minus? Oh, you're right. Well, I did take into account that f was negative. So I kind of cheated. So this is, what I'm writing now is not, what I'm writing now is actually quite ugly, because I define an f up here. But I'm implicitly using that f when I derive this divided by 1 plus. So if someone goes in and changes this equation, it doesn't work any longer. But let's write this, 9 times h. I'm sure I messed something up, but we can see. Oh, that's too many. I have to end that one and that one before I divide. That's it. Let's see if I managed to do that. It's easy to make mistakes on these. I'm just saying, in principle, I'm just solving an equation. In this case, a trivial equation. If I replace everything I know by numbers and wi plus 1 by x, this is a middle school problem, right? If you give me some other crazy f, it's not a middle school problem. Then it's Newton's method or something, right? Let's just see if it works. Did it work? Yep. Well, I guess it worked. You would have to look at the numbers to see exactly what happened. But as you can see, it's easy to make mistakes. Really ugly in the sense that this magic number here came from actually solving the equation. This is a class of method called implicit methods. Implicit because the wi plus 1 is obtained not explicit. This is an explicit method because wi plus 1 can be obtained directly as an expression from stuff you know. This is implicit in the sense that you have to solve for it. It seems easy for this case, but imagine if it's just, imagine if you can think about what happened for your pendulum on this. I'm not going to put you through that pain. But imagine running Newton on your pendulum. You would have to compute a lot of derivatives. But that's what people do in the big world. Anyway, how do you derive these methods? Right now I just showed them up. And I did derive last time a particular method of doing this. I was saying the following. Why don't you just imagine that there's an f here? So you have a bunch of fi's, fi minus 1, fi minus 2. They are not new unknowns. If you give me a wi, you just plug it into f, and you got the fi, right? So we always know the slopes. These are the slopes corresponding to those values, right? And I mentioned that Euler is kind of just saying that you're standing here, you compute an fi, and that's your slope, and you pretend that it's constant throughout your time step. That means that you're standing here, you take your slope, and you pretend it's constant, and you move there, right? And it leads to the expression wi plus h times the slope fi. That's Euler. How do you generalize this? So I mentioned the Adams method are all based on taking an old value and saying, hey, it's actually not constant. We can do better. Let's extrapolate a line through these two like that. Okay? And instead of integrating this constant, you integrate this straight line. Should be slightly better. You can keep on going. Why don't you put a parabola through these three? And you can imagine this gets more and more accurate, right? That's what these methods are based on. I did derive the straight line one on the blackboard last time. It led to the method called Adams-Bashforth 3, as opposed to 2, sorry. 2, because it's a two-step method. That is third order accurate. And it said wi plus 1 equals wi plus 3h fi minus h half. This is a quite useful method, and it's second order accurate. In the book, they show how you can do. So here's the slide summarizing this procedure. The fundamental theorem of calculus tells you that if you knew f, and you wanted to solve y prime equals f, you just integrate it from ti to ti plus 1, and you get the difference between yi plus 1 and yi. This is trivial. If you're standing at ti, and you want to get to ti plus 1, this equation tells you you want to integrate f from ti to ti plus 1. If f did not depend on y, you would be happy. It's just quadrature, right? It's just integrating, find a primitive function or whatever. The problem with ODEs is that it depends on y. So we can't do this. What Adams' methods say is that replace f by a polynomial approximation through the point you know. Okay? So you define a polynomial that interpolates a bunch of points, and you approximate the new y by the integral of this polynomial instead. And it's clear that this gives Euler for if you interpolate through one point. But then you keep on going and you get more method. In the book, you can see how they can actually derive. Now, I know you didn't like these Newton backward differences, but they come pretty handy here. It's exactly what we're doing. We fit in polynomials through a bunch of points. So you can actually derive it, and I don't have time to go through it, but they can actually write down this entire Adams-Bashforth method, and there are some coefficients coming out here. So if you need an Adams-Bashforth method, you can go in straight and just grab this method, and you'll see what coefficients come out of it. But and there are pre-computed integrals here that are just polynomials. Of course, it can be done. I wanted to point. For me, the important part is pointing out that this is a very simple procedure, and it can be done. Here are other ones. I guess this is AB. Now you've seen all of them. AB2, that's AB3, and the first one was AB4. All right? These are kind of the multistep. We'll come back to them very soon because they have a lot of things to look at, something called stability. In terms of analyzing them, we define local truncation error almost identical to, you could guess from the definition back on the one-step methods. It turns out you have to subtract all of these y's from the y ti plus 1 divided by h, and then all the f's come here. You would have guessed this. If I told you what tau is for Euler that you knew before, you can see the natural extension to the tau here. And we're going to need it in order to say something about these methods. And I'll show you how to directly calculate these taus as well. Now, there's an error control thing here. Let me first just show an example of how you can compute this truncation error directly. And it's almost easier than the Runge-Kuttas. I know many of you did not like the problem 5430. Runge-Kuttas have this issue, the nested f's. And that's actually the beauty of it, that it's a one-step method. But all these nested f's were kind of confusing. I hope you agree on that. These are less confusing. So let me show you a very simple way to derive this tau for a method that I'm making up. So here's, consider this the multi-step method. So I'm going to make up a method. Wi plus 1 equals 3Wi minus Wi minus 1 minus h times fi minus 1. Okay? And we all know that fi minus 1 is really just f of ti minus 1 comma wi minus 1. So here's the method. It doesn't look like anything you've seen. And, well, it's a method, right? So let's see if we can find tau here. Truncation error. So according to this tau, I plus 1, depends on h, sometimes we skip that if it's clear, is going to be y I plus 1 minus the constant there, 3. Actually, the way you remember tau is that you plug in the true solution y into the equation. And in this case, divide by. So you plug in the true, instead of w, you make it a y. Then you subtract over. So you get minus 3 yi, and you get plus 2 yi minus 1. And then they want us to divide that by h. And you do the same thing here, actually. You're doing, and that becomes a plus now, because there's a minus there, and the h goes away. So this is really just f I minus 1. Okay? So let's see. You can obtain this by just identifying this number as the number that we call a m minus 1, and this number to be what we call a of m minus 2. And the 1 here, 1 is what we call b m. And actually, that's a minus 1. If we go back and look at the definition of a multi-step method, well, it's here, right? It has a plus there. So since I have a minus, I guess minus 1 is the b. That's confusing. Anyway, you identify this coefficient. This uniquely categorizes your multi-step method. We have 3 numbers here. It's a 2-step method, and it fits that pattern, right? And then you can just plug into the definition. So if you're in doubt, you can just use the definition and get the tau out of it. What I remember is that you just plug in y, replace all the w's by y's, and you just and you move everything to one side and divide by h, which is the same thing. Anyway, how do you simplify this? Exactly the same as you did for the Runge-Kuttas, but it's easier because there are no nested f's. So it's just Taylor all over the place. Okay? Here's y I plus 1. Let's Taylor about ti, then this guy doesn't change. And this becomes something, this becomes something, and this becomes something. That's what we're going to do. So let me do it. It's going to be pretty quick. Taylor about ti. Let me start writing them here. So you write the yi plus 1 as yi plus h yi prime. And you always wonder how far you have to go. Sometimes you do it wrong. But I'm guessing that I will be fine just knowing those 3. And then you keep on going. There is a y minus 1, which is, of course, almost identical. You just replace all the h's by minus h, which means that the h square is plus h square. Okay? And there is one more Taylor we have to do, the f. And we do exactly the same trick as we've been doing with f's before. We say that it's really y prime at I minus 1, right? And then we do exactly this, but we put an extra prime on everything. So this is going to be yi prime minus h yi 2 primes plus h squared half of yi 3 primes, and then you stop with an h3. I think this will be fine. We don't need more terms than this. Now just plug in and cancel. So this leaves to a tau I plus 1 that is equal to yi plus 1. yi plus hy prime plus h squared half yi 2 prime plus order h3. Okay? That's yi plus 1. Then it's minus 3yi. We don't need to do anything with that. And then it's plus 2 of this guy. Let's see if I can squeeze that in here. It's yi minus hy prime plus h squared half yi 2 primes. All right? And there's an order h3 that I really wanted to put there, but it doesn't fit. It's there too, so it's fine. This divides by 8 is divided by h. And there's an f as well with a plus sign because it was minus before. So it's going to be plus this thing here. Minus hy 2 primes plus h squared half yi 3 primes. All right, that's a mess. Let's see if it works now. There's a yi plus 2 yi's minus 3 yi's. So I hope you agree that I can kill all of those. Remember, we're dividing this by h, so here's a yi prime minus 2 yi primes plus 1. And now it seems I did mess up a sign somewhere. Let me just look what I did. It should be minus the coefficient. Let's see. Don't worry. We'll find it. It's plus 2 on this one. And that gives us the minus hy prime. Oh, it's this one, of course. It's fine. I mean, I'm doing this a little too easy. But you have yi prime, h's go away. Minus 2 of them, that's minus 1, right? Plus 1, it cancels out. This is boring part. You should use a computer for these things. One more. And actually, I don't really care about the next one because I know now that it's consistent. So I don't know about the next one. I think this method is such. All I wanted to show is that it's order h2. So I can stop there. You think I'm cheating now, but it's OK. If that's all I want, it's fine, right? It might be better. It's not strict. I don't think it is better. I think it's a bad method. But I just want to show that it's order h squared, because that's what Euler was. So we would expect this to be as good as Euler. All right? So I guess I could have been more lazy with my Taylor, but I didn't know that before. But you see the whole point about this. The method takes a linear combination of these w's, right, and adds in a little bit of f. The two tricks are Taylor and use the equation. Whenever you see an f, put in a y prime. And just canceling terms, any of these taus can be obtained. So this was the direct way of obtaining a tau for a given method. Right? Now, there's a point about this method. As I said, it's order h squared, right? So actually, I was cheating a little bit. This h squared is divided by h. So right now, I just showed that it was h. I need to do one more. Sorry. You see, I want it to be h squared, so I need to show that this comes into that. All right, how many yi double primes do we have? We have an h half after we divide. We have plus 2 h half, so that's plus 1. That's going to be 3 halves, right? Minus 1. So this term does not cancel out. That's OK. That wasn't the point I wanted. I went too far there. It's order h. I don't do any more terms. Just do the ones we canceled out. And the first term I skipped was this. And it's corresponding, it's going to be an order h coming out. Anyway, that's what we had with Euler, right? Euler was order h to the 1, and it was a good method. This is not a good method. It has an extra little component to it that makes it not work. So if I just save this as a bad multi-step example and implement this method, let's see, it's a two-step method, so I can start with only 2 numbers, and we can see what happens. So the method says that wi plus 1 is 3 wi. Let's implement that method. It's going to be an h 3 wi minus 2 wi minus 1 plus minus h times f. Right? That's it. And it has to be a minus h. That's why I always put the minus down there and not there. Thank you. All right. You think it's going to work? Well, I told you it won't. But it's a little weird. I just showed you that here is a method that is accurate in the sense that you take a step here, the local truncation error is going to be relatively small. It's going to be order h. Remember what we said about Euler, that means that if you divide h by 2, this jump goes down by a factor of 4. Okay, 4 comes from local truncation error is that jump divided by h. So this method does exactly what Euler is doing. And yet, when you run it, something crazy happens. You need to look at the y-axis. It says 2 times 10 to the plus 7. This is this is blowing up. This is not what we want. It exponentially takes off. This is 1,000,000. It's just insane. Okay? So that's let's just make sure I didn't make a mistake when I implemented it. When a method is supposed to blow up, yeah, I did make a mistake. This is supposed to be f of I minus 1. I could tell because it blew up a little too much. You see, it's f of I minus 1. I took the wrong f. Still going to be bad, but I just felt it was a little too bad. All right, now we just went to 10 millionths. It's a factor of 10 better. But this is what's going to happen. It just blows up. And it's completely unbelievable. And you can imagine that imagine how people thought about this. They had Euler, and I wanted to extend it. And I said, let's start using old points. And you would think that all that matters is that this is an accurate formula in this sense, that terms cancel out in Taylor, and you get a local truncation error that gets smaller and smaller with h. And just like Euler, why isn't that a good method? It blows up. Turns out there are additional issues with multi-step methods. And that's what's happening here. And it's called stability. So what's happening is the following. I'll just show you what happens. The method, we can erase this. Just look at that method and imagine how, turns out we can analyze this by just setting f to 0. You know how we sometimes said I say that f equals y is the simplest equation. Well, something even simpler is f is equal to 0. And it will actually show you what the issues are with this method. So the method now says wi plus 1 equals 3 of wi minus 2 of wi minus 1. Okay? What is the true solution? It's a constant, right? We're solving y prime equals 0. So if you start at a constant, it's supposed to stay at that constant. So if you set w0 equal to something and w1 equal to that, the true solution is that, right? It really tells you what I said before, that prescribing 2 of these values is completely overdetermined, because they have to be the same. It's just a simpler case of what I said before. If you give one value to a differential equation, first-order differential equation, the entire solution is given. But these methods ask you to give 2. Quite confusing. Anyway, what can go bad with this equation? And the key word here is, I mean, suppose that you plug in a constant. Suppose that constant there is W0, and it's exactly equal to W1. Then you can all see that 3 of W0 minus 2 of W0 is 1 W0. It will produce a W0, and indeed you will get this. Right? So what's the issue? In order to understand the issue, you need to introduce a slight perturbation. And remember what I said? A computer always introduces some perturbation. It's just that we usually, when we just calculate some simple calculations, it doesn't matter. But what if it's a slight error here? So you do 3 of Y0 minus W0 minus 2 of W0, and the result is epsilon, 10 to the minus 16. Well, clearly this will look like it's perfect, right? But what could happen to that 10 to the minus 16? Turns out it can blow up. There will be exponential growth, and it's very easy to see. We just assume a very simple solution. Suppose that there is a solution to this. You might have done this, by the way. We teach this in new class. If you've taken Math 55, you solve recursion equations all the time. We even teach it in this new freshman course that I teach in the afternoons, Math 10b. So it's really, it was surprising how late it comes in a typical math education. We do so much calculus in freshman year that we forgot difference equation. It's like a differential equation, but it's differences instead. So you should have seen, just like for differential equation, you would assume e to the xi x, right? Now we're assuming something similar. So suppose that this wi's can be written as a constant times a lambda to the power of I. Assume that there is a number lambda that you just plug in. So if you know how to solve recursion equations, this is trivial, what I'm going to do now. You plug that in, you get c lambda to the power of I plus 1 equals 3 lambda to the power of I minus 2 lambda to the power of I minus 1. And suppose that lambda is not 0. Then, of course, this leads to the c's go away. So you get lambda squared minus 3 lambda plus 2 equals 0. OK? So if you solve this equation for your lambdas, it turns out that this is a solution to that. You see what I'm doing here? To analyze my numerical method, I'm finding an exact solution for a simple case. Just to show that it's a bad numerical method. It's going to blow up. This gives lambda equals to 1 and 2. Solve that. OK? So that means that, in particular, 2 to the I is the solution to this equation. That's bad. Very, very bad. Let's see, in particular, what happens. I'm killing the equation. Maybe that's not good. In general, you can show that the general solution here is wi. You need to choose two constants, and you get the 1 to the I, and then another constant times the 2 to the I. OK? So that's the solution to this equation. Now, if you start with exactly y0 equals w0 equals w1, of course it's going to produce constants forever, right? But suppose you have a slight perturbation. Or suppose that every time you evaluate this here, you introduce a perturbation. OK? It's clear, it should be clear to you all that you'll get maybe a slight number here, 10 to the minus 16. And you don't have to take many steps before that will blow up. So that's the issue here. It's an instability. So the solution is very simple. When you propose a multi-step method like this, you need to check that this doesn't happen. And what can we allow? What is the problem here? You can see that the 1 is not the problem. It doesn't blow up, right? The 2 was the problem. So this is called the stability criterion, that you look at these lambdas and make sure that they are not equal to 2. In fact, less than or equal to 1 in magnitude. That's the criterion. Let me show it on the slide, the definition of this. You take a multi-step method like the one we had, and you define a characteristic equation, which is this. And you need to make sure that all the roots of that characteristic equation are less than or equal to 1. And in fact, if they're equal to 1, they have to be simple. Then it satisfies a root condition, and you get a nice little theorem saying that if you satisfy the root condition, you get something called stability, which means that it's not blowing up. So it's a surprising thing, but it's quite easy solution at the end. It means in particular that our equation, my method here, violates the root condition, and it's not converting. It's not a good method. All right? Is this all new stuff for you? So summarizing, it seems like a great idea to go back in history and look at old values and try to make more accurate method. And it can be a great idea, but if you choose these numbers wrong, you can get these weird, spurious modes that blow up. And you can't use such a method. Let's look at the Adams methods. Let's take the AB, the one we did before. Where is it? What is the root condition for this guy? Well, you're going to have lambda. If you look at the definition of the root condition, you're going to get the lambda 4 from the wi plus 1. And then you have to move over to the other side. The 1 times, you get a lambda 3. And that's it, because f was 0. I guess I should have, let me copy here and then change the slide. So the Adams fourth method is wi plus 1 minus equals wi plus h times things involving f, right? If you look at the root condition, it said you need to form a characteristic polynomial that is lambda to the m, which is the order of the method. Then you do minus the first coefficient times lambda to the m minus 1. That's a 1. And in principle, there could be other wi's here, but there's not. So this is the equation to solve. Okay? And the roots of this are 0 and 1. And 0 appears multiple times. Does it satisfy the root condition? Yes. All the roots are less than or equal to 1, and the ones that are equal to 1 are simple. Okay? That implies that it's stable from the theorem. So it's really just an extra check. But if you make up a multi-step method, you might get a bad method. Again, the theorem says that if you take a multi-step method, you check stability, and we will also check that it's accurate, of course, namely that tau is order h, or more accurate. How about one-step methods? Do they have this issue? Here's a theorem telling you that one-step methods never have this problem. Now I'm back at Runge-Kuttas, basically. Or in general, one-step methods. So it's a little complicated theorem, but it says something very similar to what we did with Euler before. That if you try to solve y prime equals f by a one-step method, what is a one-step method? It's something where you can write wi plus 1 obtained only from wi. Then things are pretty good. You need to assume that this phi, whatever you set it up to be, is Lipschitz, but that's fairly easy. And that implies stability. So this method is stable. Okay? Just like Adams-Bashford was stable, it happened to be, but I could choose wi, so it's not, right? Like I did in that bad example. The one-step method never had that possibility, which means that all you have to check is that you have a tau that is h or better. So in particular, when we were back in the Runge-Kuttas section, we showed that, for example, we did a derivation. We showed that a method was order h squared tau. That means that it's going to be convergent. There are no stability issues. So one-step methods are better than that. Here's a generalization of the expression you had from Euler. You might remember this exponential. And back then, we had an h here. And there was also an m, big M, divided by 2. That was tau. So this is exactly what we got with Euler before. And it turns out it's true for any one-step method. So the Runge-Kuttas have a huge advantage in this. That when you design them, you just make sure tau is small. If you got a result like this from a Runge-Kuttas method, you could immediately say, based on this theorem, that it's a convergent method. It has no issues, and it could never blow up like this one did. So that's good. I threw out a few words. Let me go back just to define them. I think I said consistent without telling you what it is. Consistent basically means that tau is small. More precisely, it means this. That as h goes to 0, tau goes to 0. Okay? The idea here is that this is the error you're making as you're taking a step. It has to get smaller as the step shrinks. Okay? We call that consistency. What you just saw is that that's not enough for a multi-step method, because it can still be a bad method. So what we actually want is convergence. And that's another word I've been using a lot, which basically, I think you know what it means. It means that the numerical solution converges to the true solution, and it can be defined in this way. If you look at the numerical solution, this is what you plot. Every time I ask you to plot these log-log plots, you're looking at the numerical solution minus the true solution. And if that gets smaller and smaller, when h gets smaller, you have a convergent method. All right? Stability is a tricky concept. There are many parts of it, and it's a pretty fundamental part of studying these multi-step methods. It's not that important for one-step method because of this theorem. So you just get rid of stability immediately. But for multi-step, it's a bigger issue. All right, let me trace back, because I jumped over because I thought it was better to do all the multi-steps at once. We have the multi-step methods, a bunch of them, and derive them. They do have a section on error control for this, just like we did 2 different methods for Runge-Kutta. You can do the same with these methods. All right? And what they do is actually something slightly different. So let's look at it just because they do it. You can do exactly what we did for that Runge-Kutta Fehlberg that you're going to be using for your homework, in the sense that you define one method that is more accurate than the other one. But there is another thing you can do. You can actually come up with 2 methods. One that is here called, well, we don't have a notation for it. The error term has a hat and the other one has a twiddle. So you have 2 methods for finding a W. I guess this superscript 0 here is the actual method. So you have a method W superscript 0. And you have another method. And in this case, they have the same order of error here. Do you think you can derive an error from that? That's the question. Let me remind you that back on the Runge-Kutta, we did something very simple. We said that we have 2 methods, and one was a whole order more accurate than the other one. So back then, we did 2 methods that were, the notation was this, Runge-Kutta here. We had 2 methods, and the way I wrote it was to say that one of them was order, well, it's actually here. I don't have to write it. One of them was, can I mark here? How do I mark? Select tool. I should have a nice little painting. Select. Now I can mark. One of them has order hn, right? And the other one was one more order accurate. When you expand these equations, you can get easily that you can estimate the order in one by subtracting these equations. You can estimate the order in the inaccurate ones by simply just subtracting them. And there was an extra divided by h. What if you go back here and say that that was not the case? Namely that this tau I plus 1 and this tau twiddle I plus 1 had the same order of accuracy. Would that give me information? Or in other words, you have 2 methods of the same order, and you take a step with each. Is that information in there for telling you what the tau is? So in a way, here's a picture. You have one method, let's say Euler, that does that. Okay? This is what we call Wi plus 1, 0. We all know what it means to be order h. We know that if you divide h by 2, you're going to go, this error is going to be 1/4 of that, but this is going to scale linearly. So we're going to end up exactly there if we divide h by 2. Now I give you another method with exactly that property. So let's say I have another method that does whatever to produce this number, and we call it Wi plus 1. 2 different methods. Okay? Is that enough for finding out an estimate of this error here? The key here is that you need to know one more thing than just the order method. You need to know the constant in front of it. So if I tell you that this here has a constant of h divided by 2 or something, and this here is minus h by 2, and this is plus h over 2, that should be enough information to solve out for this jump here. This is just an intuition. In terms of the equations, this is how you write it. If you give me 2 methods, you can say that the local truncation error, this is tau for the first method, this is tau for the other one. There's a constant, and there's of course this high derivative, but the key is this. So often we just say order h4, right? Order h4 means that there's a constant in front of it. And you can show, based on Taylor, that that constant involves a higher derivative of y. Now, if you have another method with a different constant, turns out that then you can solve for an estimate of this tau. I'm not sure if the intuition, I guess it's a little if it's not clear that it's intuitive. So let's just do the algebra. We assume that these two are the same, and we basically just subtract these equations. Again, we get that you can subtract the two w's that you get, and you can get an estimate for, turns out that it's not immediately satisfying. You have to solve this equation. So this 3/8 here comes from subtracting these two numbers. And the end result is that you can estimate the tau, just like before, by this over h, but it's times a constant. It's really, I don't know why they present it in this way. It's because people do it this way. It's very common for multi-step methods to have two methods of the same order, and you use the other one to monitor the error in this one, and it ends up being a slightly different expression. It's really fundamentally almost the same as Runge-Kuttas, where they do something much easier, namely having a more accurate method to monitor the error in the less accurate method. When all this is done, you remember this Q, right? The rest is the same. You can change the step size, etc. I'd like to mention one thing. Do you think with a multi-step method, it's a good idea to change step size? What happens if you change step size with a multi-step method? So you struggled a lot to collect a bunch of W's. I minus 1, I minus 2, I minus 3. And they are, of course, separated by an h. And you would like to take a step up to wi plus 1. OK? Remember what the setting was, that you're telling me that you want a tolerance of epsilon 10 to the minus 3. And then you have this method of estimating the error there. And I tell you it's greater than 10 to the minus 3. It's 10 to the minus 2. OK? Just like before, of course, you can compute a little q, so you can change the step size, so it gets more accurate. But what happens to the method if you change the step size? Suppose I tell you I don't like h. I want to do h 75% of h. All the w's are not working any longer. Remember, a multi-step methods need these four numbers spaced by h in order to produce this new number. If you now change h, you don't have those new numbers. In particular, if you want to change h to be, let's say, this, let's do something more extreme. Let's say you want to change h to be this. Then you need these four numbers instead. 1, 2, 3, 4. You don't have those numbers. It's a big problem. How do you think they solved it? So there are a few good things. If you divide by 2, you could reuse some of them. You see that, right? That's a hack. If you multiply it by 2, it's actually all good if you have enough history. If you're having this h and you're saying, oh, I want h to be twice, then you can just grab that one, and that one, and then you keep a lot of them old, and that will actually work. So many of these codes are doing these things of always just dividing by 2 or multiplying by 2. Another trick is, of course, to interpolate here. Put some, chapter 3. Let's put the polynomial and evaluate these things. And there are some issues with that. Overall, I think I can summarize these multi-step methods as having issues. And the issues are stability. The issues are that when we want to change the step size, we need this long history of data, and it's going to change when you change step size. And I started off saying maybe the most fundamental issue, you don't know how to start. We cheated in my little example by knowing the true solution for 4 steps. But in general, you're standing at time 0, and you want to take a step to time 1, and you just cannot do it with a multi-step method. So these are issues. Having said that, the methods are pretty competitive, so people overcome these issues in various ways. But Josie, this is all I wanted to say about that. I'm skipping this extrapolation method. I know it's going pretty fast here. So let's slow down. Are you guys cool about all this? Any questions on it? I guess it's a tough schedule. It's There's more important stuff. We did 5.10, and I'm going to show you a little bit more about the one-step methods. But I'd like to give you perspective on the whole thing. And there are really two big classes of the methods. There are the Runge-Kuttas, which are one-step method, and there are the multi-steps. And I'm listing pros and cons. I don't think I said too many bad things about the Runge-Kutta, and that's because they are pretty good. Maybe I did say that when we analyzed them, this is much easier. I know it looks messy, but it's really just fairly straightforward tailors equispaced by h. When you do problem 5.430 for your homework for today, you get a lot of weird nested f's and stuff. They don't show up here. The analysis of these methods and the design of them is very natural. Multi-steps are good in that sense. There's a slide here that they emphasize in the book, and I might have assigned a problem on it. It's quite common with something called a predictor-corrector method. What they do is that they overcome the issue with Adams-Moulton, where we had to solve an equation, remember, to get this thing out. It's a hack to say, let's take a step with one method, Adams-Bashforth, get a number that we're going to throw away later, but we use it on the right-hand side of the Adams-Moulton method. You see how that turns Adams-Moulton into an explicit method? Because now you pretend that you know the wi plus 1 in the right-hand side. It's a class of methods, and they have certain properties, and it's actually used a lot. So I think it's worth mentioning. This is just to avoid the problem we had when I had to divide by 1 plus 9/8/24. If you, instead of solving for it like I did, just predict it using another method, and there's an error in that, of course, but it's accurate, then people get away with it. Anyway, that's what we did with those methods. This chapter we skip, and this one we did before the higher order systems. So let me go back to just this theorem here. Convergence over the one-step method. So this, I mentioned before that this was fairly fundamental. It tells you that this is, and the thing I did not mention is, how on earth can this include anything else than Euler? I'm saying that you need to write the method on the form wi plus 1 equals wi plus h times a phi involving wi only. Okay? So you should see that Euler fits that pattern if you set phi equals to f. That is Euler. Let's look at another method I have and see if you can see that it also fits that pattern. It's actually the first Runge-Kutta method we did. So I want to go back and just derive the same for that, and we basically, through this theorem, we'll obtain that it's going to be a convergent method. So we're doing the midpoint method. It was wi plus 1 equals wi plus h times f of ti plus h half wi plus h half f ti wi. Remember this one? wi plus h half f of ti wi. So that's the method. That's the first Runge-Kutta method we derived. It was the one where you took half a step of Euler. This is half a step of Euler. And then you use that slope to take a full step of Euler, and it was more accurate. So this is a great method. We tested it, and it's all good. How here's the question. Write as wi plus 1 equals wi plus h times some sort of phi of ti, what order? Wi, right? Yeah, comma wi h. And it's clear that that's the case by just setting phi of ty, I'm going to call it y now. No, w is fine. Equal to this whole expression except the h. So it's f of t plus h half, comma w plus h half f of t, comma w. All right? It turns out that with a complicated phi like this, you can really write this method like this. I unnested everything, right, and put it in this form. Do you see that this is a one-step method? Many people don't agree that Runge-Kuttas are a one-step method because it looks like you're taking two of these steps, right? But the definition of one step is really that it can be written on this form. Namely, you give me wi, and I evaluate this function, and I can give you wi plus 1. So that's what we're going to do. Now, what does the theorem say? it says that this phi must be Lipschitz in W. Is it? Well, I claim that if f is Lipschitz, then phi is Lipschitz. Why do I say that? What is phi? It's f of something involving f itself. Well, these are things you can show with various continuity. You certainly know it for continuity. That if you take a continuous function and you nest it, so let's say a continuous function, adding to a continuous function gives you a continuous function. Multiplying them gives you a continuous function. Nesting them gives you a continuous function. If you do g of h of x, and they're all continuous, the resulting is continuous. And the same thing is going to happen with Lipschitz. So it all comes just down to f. We're putting it together in a weird way, but it's all good. But we can show it directly by just looking at phi t comma w. Remember what Lipschitz said. It says make a jump in the variable where you're looking for Lipschitz continuity. And look at the corresponding jump in the function value. Okay? Now, if you assume that f is Lipschitz with constant big L, can you see that this phi is going to be Lipschitz? Well, let's plug it in. So it is here, right? So this is just plugging in f of t plus h half, comma w plus h half f of t comma w. Minus f of exactly the same thing, comma w bar plus h half t comma w bar. And absolute value. Okay? Now how am I going to turn this into Lipschitz? Well, f was Lipschitz with constant L, right? So now you do Lipschitz on f. So you have to put these together and say that this is really a jump in an f for a corresponding jump in the w argument to f. You see that, right? I'm taking f, it's the same time. The time doesn't matter. It's f evaluated at this number minus f evaluated at that number. Lipschitz continuity tells you that that's less than or equal to L times the corresponding jump in those numbers. So it's really just w plus h half f minus w bar minus h half, there's an f here, f of t comma w bar. All right? All right, how am I going to now keep on showing that it's Lipschitz? Remember, I want to show that this big function can be bounded by a new L times the jump in w's. And it's starting off well here. Here's a w minus w bar, right? But I need to address this situation. There's another f. Do you see what I'm going to do with the f? Just Lipschitz again. So first, let's do a triangle inequality. There's certainly a w minus w bar coming out of there. But then you have this h half of f of t comma w minus f of t comma w bar. Right? I did the triangle inequality just grouping terms. So I'm getting there. I want to show that this is less than or equal to a new L times the jump in w. And you see, I'm going to need a new Lipschitz application on these f's to do that. So this is less than or equal to L times jump in w's plus h half, and this is really just less than or equal to L times the jump in w's. Right? So what's the new Lipschitz constant? Is equal to L plus h half L square multiplying w minus w bar. I showed that if you take your phi function and send in different w's, w and w bar, it can be bounded by a number times the jump in the w's. That is Lipschitz continuity for the function phi. Do you think you need to do this every time? I kind of hand-wavingly said that if you nest if you nest Lipschitz continuous function, the result is going to be Lipschitz. That's what you should be using, right? So we know that this is going to happen all the time, unless you come up with a phi here that would be introducing, discontinuities and weird stuff, right? But as long as this phi is just nesting f's in a nice way, this can happen. This here is, of course, a new Lipschitz constant for phi. Doesn't really matter what it is, unless you want to plug it into that equation. So really, if you want an error estimate coming out of this equation, you see that this L here now is the Lipschitz L, is not my L, it's the Lipschitz for the phi function, L plus L square h half. So that's how we can do all these things. All right, too much stuff. Any questions on this? Are you shocked? You might want to read the book. The book is good in this chapter, I think. There are good and bad parts, but this is, I'm following the book quite closely. All right? No office hours tomorrow, but office hours now if you want to come. Thank you.